Hey guys, welcome back to CMTEQ channel, where we make power system concepts simple and accessible for everyone. In this tutorial, which is tutorial 3 on our series of tutorial on transmission line calculations, we're going to dive into the nominal T model. Well, why the nominal T model? Well, when you look at this transmission line pylon here with 3 wire, basically 3 conductors, line 1, line 2, line 3, we've got a representation of C1, C2, which are capacitance of the line. Now, the capacitance here in the transmission line is inherent to its physical construction, okay? It naturally exists between the conductors and the ground. Due to the separation, like the distance between this line and this line, and the physical properties of the insulation and so forth. Now, in reality, this capacitance is basically distributed continuously along the length of the line. So you're going to have another capacitor here, you can call it C3, and here you can call it C4, and these will go all the way for your medium transmission line 250, 80 kilometers, right? Now, here is where the problem is. For calculation purpose, especially in medium length for 80 to 250, you cannot ignore line capacitance. For simple short transmission line, you can actually just ignore it and just model it as a series impedance of the line, like in the first tutorial. But for medium transmission line, you cannot ignore the capacitance of the line. So what do engineers do? They try to make things simple. So they create model. Okay, so we've got the pi model, which I've done on the previous tutorial, and this is the nominal T model. This model is simply because modeling this distributed capacitance directly to solve our problem becomes a very complex issue. Okay, we cannot, it's a mathematical nightmare. How are you going to start measuring and calculating and adding up all these capacitance to come to your final transmission line parameters calculation? It's impossible. So instead of doing that, we just lumped the transmission line capacitance at the center of the line, like you see here. These capacitance basically just become a single capacitance at the midpoint center of the line. This is a mathematical simplification to just allow us to calculate the voltage drop across the line and find the sending end current as well as the receiving end current parameters and whatever parameter that you want to work out in this transmission line model. Great. Now, having said that, I hope you now have the necessary background information where this nominal T model is coming from. Now let's start solving this problem. So reading and understanding your problem statement is very crucial to avoid you making mistake, knowing exactly the known and the unknown parameters. So we got a 3-phase 50 Hertz overhead transmission line like what we're seeing here. Now the power at the receiving end here, that's PR, 100 megawatt. The line voltage, 110. Power factor, 0.8, lagging, and active load. Okay, now we've got a resistance per phase here, 30 ohm and 40 ohm, and these capacitance, the lumped capacitors at the midpoint here. Now we need to calculate the voltage, current, and the power factor at the sending end. So obviously, like we did before, the first step here is to establish what you have, basically your given data, active power, power factor, and determine the angle at your receiving end. We explained it in the previous tutorial. Then at the receiving end, we've got a line voltage of 110 kilovolt and the per phase parameters. Okay, now this is where it gets interesting. Now we know that the parameters at the line here, they were given per phase as 30 ohm for the resistance and 40 ohm for the reactance. Okay, these are the series impedance. Now because this is a T model, we have to divide it because each series impedance is going to fall at each half of the transmission line, okay, while the capacitance of the line is modeled at the center of the line. That is why we've got the Z per phase here to be 15 plus 20J. Okay, so that is for this section and this section as well. Same parameter. Now when you work it out, you've got 25 with an angle of 53,13 degree ohm. Moving on, the shunt reactance, obviously XC 600 with an angle of negative 90. Step 1, convert the line voltage to phase voltage. Very simple. So that is 63.5 kilovolt. Step 2, calculate the current at the receiving end. Okay, now this is your current at the receiving end flowing to the load. Okay, now to calculate this current is very simple. You just need to know what is the voltage that is driving this current, and that voltage is already given to us here as 110 kilovolts. So very simple, we can deduce and calculate the current at the receiving end using the 100 megawatt of power and the line voltage. I already explained this formula in the previous tutorial. So we find this current here of 656.08 amp. Okay, now this current have an angle here that is negative 36.87. So our phase angle for the current give us the total statement for the receiving end current. Now we continue with the step 3, which is to calculate the voltage across VC. Okay, now if we didn't have this line impedance here at this section, we will just deduce that this voltage VC is the same as this voltage at the receiving end, obviously per phase parameter. Now because we've got this series impedance on this section of the line, we have to take the voltage drop across this series impedance and add it to the receiving end voltage to actually get the voltage across the lumped capacitance. Okay, so we can name this voltage as VZ2, okay, which means at this section here, this is going to be VZ1. You can name it whatever you want to name it. Okay, so having said that, we can continue. By the way, please thumbs up if you find this tutorial useful. I thank you so very much. Then that means V per phase is VR plus VZ2. That means VZ2 is actually IR times the series impedance, because the current flowing here is exactly the same current flowing there. Very simple, Ohm's law there. Okay, and we can calculate VZ2, which is the current times the impedance per phase. And one thing to remember is this line current, okay, it is equal to the phase current in a star connected transmission line. I explained that in the previous tutorial. Okay, now moving on, we find our VZ2. We continue, then that means VC per phase is then the combination of this small voltage drop plus the receiving volt per phase, which is 63.5 kilovolt. Obviously, angle is 0 degree, and this one, the angle is 16.26 degree. So we find a VC per phase that is equal to 79.38 with an angle of 3.3 degree kilovolt. Now we move on to step 4. Okay, now we know what is the voltage here across this capacitance, so which means this voltage is actually going to help us find the current through the capacitance. Okay, that means this voltage is driving this current. Remember, the voltage is a pressure that drives the current. Now we're going to find our IC here. Very simple, and that is VC per phase divided by XC. Straightforward, we found the current IC 132.3 with an angle of 93.3 degrees amp. Continuing, step 5. Now, since we now find this current, again, Kirchhoff current law, so which means I sending here must then be equal to the sum of current leaving this particular node here. So that is IC plus IR as per the previous tutorial. And that means IS, okay, is equal to IR, which is this particular current per phase, okay, plus the current IC, which we basically calculated here. So we find this current IS to be the sending end current. Straightforward, very simple, guys, but you have to understand the methodology that you are doing here so that you don't make mistakes. Now we move on to step 6, voltage at the sending end. Now since we now know what is the current across these series impedance here, it is now very easy for us to calculate VZ1. Okay, that way we can take this voltage and add it to this voltage to find the voltage at the sending end. There you have it, guys. So very simple. Then you've got your problem solved and get the full marks. Okay, so moving on, Vsend is obviously Vc with an angle, Vc theta with an angle, plus Vz1 with an angle. Okay, Vz1 is Is times Z per phase at that section of the line. We know it is exactly the same here. Okay, and the current Is, we just found it there. Then we find Vz1 to be equal to 14.5 with an angle of 26,33 degrees kilovolt. And from here we can go ahead and calculate our Vsend by simply adding Vz1 plus the Vc that we found here. Okay, 79.38. There it is, plus the Vz1 that we found there, and we can actually calculate Vsending per phase to be 92.9 with an angle of 6.8 degree. And if you want to calculate the Vsending of the line, you just have to basically multiply this value with the square root of 3, and that's going to give you the sending end voltage of the line. Great stuff. Now moving on, step 7, the power factor at the sending end. Now this is very important because the power factor at the sending end is what's going to help you find the power at the sending end. Okay, and once you have the power at the sending end, like we said in the previous tutorial, you can find the efficiency and many other parameters that are necessary for your line. And the power factor at the sending end is always the combination of the angle of the sending end current with the angle of the sending end voltage. Okay, so that's cos of angle between Is and Vs. Okay, so if you have to compute this with your calculator, is very simple. So it's cos of 26.8 plus 6.8, which is the angle here of the sending end voltage per phase. Okay, you close your bracket, equal, then you're going to find 0.83. Now this is the power factor which is lagging at the sending end of the line. Okay, now from here, like I've said earlier, you can get the power at the sending end and get the efficiencies. You already know what is the power at the receiving end, 100 megawatt. So that is it, guys, for this tutorial. I hope you found it useful, and if so, please make sure you give it a thumbs up. Subscribe to CMTEQ channel so you not going to miss more tutorial of this nature, unlocking more power system concept for you. Thank you so much for joining. Until next time, cheers.